Hello and welcome back. Thanks for hanging out with me for a little bit. So last time we talked about the CNC machine. We just went through real brief objectives, what it's going to be used for, and some components, which is basically as cheap as possible. So today I wanted to talk a little bit more about materials and what materials we have at our disposal. So a lot of times I'll be on CNC Zone and I'll see like, oh, you got to use cast iron, or you got to go to the old iron or whatever, because it's the best for CNC machines. But frankly, I don't have a kiln. So what do I have at my disposal? Well, I have some steel, just normal 1018 carbon steel, or some aluminum, specifically 6061. Also, epoxy granite is another option, but again, it's just so expensive and just not worth it. So today I want to do the old death match between steel and aluminum for a CNC machine. Looking at material properties, there's this graph that shows what is called Hooke's law. So here in this linear part, which just means that it's a straight line, that's what linear means. It's called the elastic region. The after that is called the plastic region. So elastic just means that when you bend it, it'll return to its shape. And plastic means that when you bend it, once you bend it so far, it won't return to its original shape. So because we don't want it to deform, we will only be designing and looking at the elastic region. The slope of this line is called Young's modulus, or the modulus of elasticity. I was taught it's Young's modulus. Basically, it describes how a material will respond to forces applied to it. Young's modulus then will show us the rigidity of a certain material. We are going to neglect shear modulus in all of this. Shear modulus is basically like a bolt and when it'll break. But here we just want to know Young's modulus. That's what we're going to look at. So starting off with Young's modulus, I want to look at cast iron since that's kind of the standard. Young's modulus for cast iron is 81,496 megapascals. And of course we're doing our death match between steel 1018 hot rolled and aluminum 6061. Steel 1018 hot rolled is 207,000 megapascals. And aluminum 6061 is 68,900 megapascals. Okay, so how hard could it be, right? Let's just choose steel. It is like close to 3 times as strong as aluminum. All right, so hold on just a second. Why, throughout the history of milling machines, have most of the good ones ever been made of cast iron? We got Bridgeports, we got Tormach. All of these are made out of cast iron. Why? So Fusion 360 has a full suite of different things that it does. It's a model. We have a good parametric modeler. And then we also have rendering, we have animation. Simulation and cam are my 2 favorites. Today we're going to look at simulation. So let's just run a quick static simulation. I've heard that it is around 50 pounds is a normal cutting force for these types of machines, and so we're going to look at the deformation 50 pounds right on this tip here. All of these parts are made out of steel as the material, except for the bit which I inserted carbide. Okay, to get started here, all you got to do is you got to click study. Mine's a little bit messed up. Oh, there we go. Static stress is what we're going to do here. Go okay. Super simple this. Okay, so after you have your study created and we're in the study, we just need to add some constraints and then some loads. Then we'll do generate contacts, which is going to take a while. But for us here, we're just going to add constraints to the bottoms. Bottoms of these two, because that's pretty much what it'll sit on. So that's just where it's rigid or where it's not going to move. Okay. And then we're going to apply a load. Our load is going to be applied to the tip of this tool. And it will be 50 pounds in the Y direction. And click OK. Okay, so I've already solved this on my own before. It takes a long time to solve. It takes like 45 minutes on my computer. But anyways, as you can see here, most of the deformation is in the tool. If we go down here, outside of the tool, there is, what does it say? 0.8 of a thou. So what that tells me is that the tool will break before anything happens to the machine, before the machine deformation becomes more of an issue. And so that's very interesting. Why did we build this so beefy to begin with? This whole idea of beef. Why did we do that? Well, next time I'm going to talk a little bit more about that and why we do that.